Now let's try a work energy problem with tension. So as always, we'll start with a picture. We've got a mass. We know the mass is 0.4 kilograms. It's hanging on a rope that's coming down off a pulley. All right, so that means we got a pulley here and the rope's coming down like that. And who knows what's going on the other side? They don't tell us. All right, so we got the mass hanging on a rope that's coming down off a pulley. These guys are ideal. So I guess that means they don't have mass themselves, at least compared to this guy. There's no friction going on. The rope isn't going to be stretchy and doing weird rubber bandy things. So that's all good. Oh, and they tell us the tension in the rope. The tension in the rope is 2 newtons. And it's constant, so that's nice as well. All right, if the mass starts from rest, okay, so the initial velocity is 0. How fast is the mass going after it falls? 33 centimeters. So I guess after it goes down this amount, 33 centimeters, and we want to know how fast is it going here. And looking at this, I got newtons, kilograms. Let's change this to standard units as well. So that'll be meters divided by 100. So let's just move the decimal place over 2. So 0.33 meters. Okay, so we've got forces, we've got speeds and distance. So we might do this using the Newtonian model, but let's try it out with the work and energy model. So the equation we'll always use for work and energy is we find the net work and we set that equal to the change in the kinetic energy. And we say, yeah, this seems like it'll be right. Oh, I misspoke. The work energy theorem is actually, this is the change in all the energy. But the only energy that we got going on here, at least how we're thinking about it now, is kinetic energy. All right, so to find the net work, we're going to have a free body diagram for our mass. So what are the forces acting on it? Definitely tension. We've got tension that's going up and it's got mass. So there's going to be the force of gravity. We know the gravity force is always equal to the mass times g, that 9.8 meters per second squared. And now we need to figure out, do these guys do work? So that means we need to know what is the displacement. Do that in a different color. So the displacement is down like this. It goes down 0.33 meters. All right, so that means that gravity is going to do positive work because that force is in the direction of the displacement. And that means tension is going to do negative work because the force of tension is opposite direction. And we don't have any forces which are perpendicular or only have some component in the direction of displacement. So we don't have to worry too much about our dot product even. And this guy is constant and that guy is constant. So when we go to do the work, we can use the simpler equation for work. All right, so before we get too excited, we'll say the work, that's the sum of all the works done by the various force. So in this case, that's gravity and tension. Work in general is always equal to the force dotted with the displacement if it's constant, as these forces are, and the path, the displacement, is a straight line. So we can use this simpler equation for work. There's the work done by gravity. Here's the work done by tension. Okay, so gravity, it's down, it's the magnitude of the gravity force and the magnitude of the displacement and the angle between them. I will call it theta sub g, but that angle is 0 because they're pointed in the same direction. And cosine of 0 is 1, so the work done by gravity is just the force of gravity times the displacement times positive 1. That's the cosine of the angle. Okay, so that's gravity work. Now let's look at tension work. So the dot product is the tension magnitude times the displacement magnitude times the cosine of the angle between them. but this angle is 180 degrees because tension is pointing that way and displacement is pointing in the opposite direction. And cosine of 180 degrees, that's -1. So when we do this out, we'll have tension times d, the displacement, times the cosine of 180 degrees, which is -1. And those are our net works. So let's write this a little neater. Gravity force, oh, and I guess we know that gravity force is mg. That's the force due to gravity. Displacement minus tension times displacement. And then we back all the way up to our original equation. We say, that's equal to the change in kinetic energy. And the change in kinetic energy is the initial, the difference between the final kinetic energy, so that is K final, minus the initial kinetic energy. So that is K initial. And we know the initial velocity is 0. Sweet, so let's plug that in. Nothing else changes. This guy is 0 squared, but 0 squared is still 0, and 0 times anything else, all of that is 0, so everything here is equal to 0, and we are left with just the final velocity. Let me write that all the way down. Okay, so what are we actually solving for? We are solving for the final velocity. So now that we've got our equation all set, let's go ahead and isolate the final velocity. So we got mass times g times that distance that it fell, minus the tension times d, so gravity down doing positive work, tension up doing negative work in this case because it's displacing down. We'll multiply by 2, both sides of the equation. We'll divide by m, both sides of the equation. The mass will cancel here, the 2 will cancel there. Very tempting to cancel the mass here, but we can't do it because there's no mass in this term. So we will have, let's distribute the 2. Get minus 2 tension all over the mass. That's equal to the final speed squared. And we'll just split this up. So that'll be 2 mgd over m minus 2 tension displacement over m equals the final velocity squared. All right, now we can cancel this mass because we just have term with mass up here, but we can't cancel that mass. And we take the square root of both sides of the equations. So we get 2 times g times the difference in height, that displacement, minus 2 times the tension times d over the mass, all of that square rooted, equals the final speed. And again, it could be up or down from the math, because when we take the square root, we don't know which one is correct. And looking at here, we haven't actually said which way is positive or negative, so let's just bypass that whole argument and say it's going to be going down. Whether that's positive or negative doesn't matter. This will be the magnitude, and that'll be the direction, down. All right, so now let's plug in, get our numbers. 2 times gravity, 9.8 meters per second squared. The displacement is 0.33 meters. Minus 2 times the tension, that's 2 newtons. The displacement, 0.33 meters, over the mass, that is 0.4 kilograms. Square root all of that. Run out of a little space, so we need a new sheet of paper to work on. There we go. Okay. So this first term here, that is gonna be, let's see, 2 times 9.8 times 0.33. Get our calculator. That is gonna be 6.468. And units, meters over second squared times meters. So that'll be meters squared over second squared. Minus the second term, 2 times 2 over 0.4, so that'll be 4 over 0.4, so over 0.1. So then when we divide 0.33 by that, we get 3.3. You can check it with your calculator if you want. And then newtons times meters over kilograms. Let's go off and solve that over here. So Newton meters over kilograms. Newtons are kilograms meters over seconds squared. That was the newtons multiplied by the meters over the kilograms. The kilograms cancel. So we got meters times meters. That's going to be meters squared over seconds squared. Good. Same units here and there. So we can actually combine those with subtraction. And we take the square root of the whole thing. Okay, so 3, this guy, let's see, that'll be 3.168 meters squared over seconds squared. Take the square root of that. And this, we'll go ahead and get our calculator out. All right, so that will be, when we take the square root, that'll be 1.78, and meters squared square root is meters over seconds squared square root is seconds, which is good. That's what we want in terms of units. All right, so that is how you would do a work energy problem if you were involving tension.